Ben, we're going to start off with a little question. Which of these rocks, the big one or the small one, do you think will fall faster?
This one has more mass, so I think it will fall faster.
That's an interesting point, Ben. Let's go figure this out. We'll turn to our assistant, Mr. Dr. Professor Sam Lane, to do the experiment for us. Sam? Sam's going to go drop it off that building right there, and we'll see which one falls faster. Turn up.
The big one's in my right hand, the small one's in my left hand. Let's see.
They hit the ground at the same time!
So, Ben, are you surprised they hit the ground at the same time?
So surprised.
Yeah, me too. Except not really. Because they fall at the same rate. On Earth, all objects fall with the same acceleration due to gravity.
That's crazy.
It really is. Science is wacky.
You guys suck.
Now we're going to go back into the classroom and figure out where this equation comes from.
Sounds like a plan.
So, Ben, what do you recall about gravity?
It makes things fall to the ground?
Yes, it does do that. But in fact, gravity is more than just that. It's a relation between all objects with mass. So, do you remember any formulas describing gravity?
Nope.
Maybe in Physics 1?
Nope.
Well, do you remember Newton's second law? That force equals mass times acceleration?
Oh yeah, I remember that.
Well, gravity is actually just a force. And on Earth, we have the formula F of gravity equals mass times g, which is a gravitational constant of acceleration, which on Earth, close to the surface, is equal to 9.8 approximately meters per second, or meters per second squared. Does that make sense?
Yeah.
But you might be wondering, why is g constant? Why is there constant acceleration due to gravity?
Oh yeah, like with the thing outside.
Exactly. So, when we look at this equation, it's actually part of a bigger equation of gravity. Dun, dun, dun. So, Ben, remember how I said earlier that gravity is the attraction between all objects with mass?
Yeah.
So what do you think comes into play when you're talking about the force of gravity?
All objects.
Yes. So, but what properties of the objects are going to affect the force of gravity?
Their mass?
Good. So the mass of two objects will actually, gravity depends on the mass of two objects, m1 and m2. We'll call it force of gravity. And then this is going to be our proportional sign. What else do you think it depends on?
The distance.
Yes, Ben. Very good. But do you think as it gets farther away from an object, the force is going to be stronger or weaker?
Weaker?
Yes, it is going to be weaker. So we're going to put the masses over the distance. And it's actually the distance squared. And when we put r squared, r is the distance between the center of masses of two objects. This is r, and this is m1, and this is m2. So r is the distance between them, m1 is the mass of one of them, and m2 is the mass of the other one. So we have that force of gravity is proportional to m1 times m2 over the distance between their centers squared. But you might be wondering, well, can't we get a specific equation for this?
That's exactly what I'm wondering.
Good, good. You're really getting good at this physics mumbo jumbo. So, we actually have force of gravity equal to G, which is the universal gravitational constant, times m1, m2 over r squared.
Is that big G the same as that small g?
No, that's a good question. But when we look at this big G, on Earth, the mass of the Earth is constant, right?
Yes.
So this is always going to be the same when we're on Earth, the mass of one of the objects. And then when we're near Earth, everything that's near the surface is going to be marginally different from the radius of the Earth, but in comparison to the radius of the Earth, it's almost no distance. So r squared is going to be more or less constant when you're close to the surface of the Earth. And g is a gravitational constant, so we know that that's constant. So this whole deal right here is actually constant, more or less, when you're on the surface of the Earth, or near the surface of the Earth. And this equals little g, which gives us that equation that the force of gravity on Earth, or near the surface of the Earth, is equal to m times m2, which is really the mass of the object near the surface of the Earth, times g.
Oh, I get it. So g times m1 over r squared equals little g.
Yes, Ben, very good. So now, whoops, dropped the physics, see? That's a force of gravity too.
Wow.
So now we can see how this big relationship that explains the motion of planets and the sun and the moon is actually the same as this same equation that we learned in Physics 1.
Wow. Physics is amazing.
It really is, Ben. So, Ben, you may be wondering how exactly we get little g from big G.
I am wondering that.
Well, little g, we'll call him little g, you know, like little B, little Wayne, little Romeo, but this guy's the original gangster, so little g actually comes from big G, like we said earlier. So, do you remember our equation for universal gravitation?
Big G.
F of g,
Oh,
or F of gravity equals,
F of gravity equals big G times m1 times m2 over r squared.
nice! You remembered the squared and everything. And remember how I said that on Earth, m1, r squared, and g are constant?
Yeah.
So, we're going to use this to figure out little g. So, what is g?
G is 6.67 times 10 to the negative 11th meters cubed. Oh, 10 to the negative 11th. Sorry, I'm going too fast for you.
10 to the negative 11th.
Meters cubed over kilogram second squared.
Okay. Then you multiply that by the mass of the Earth. What's the mass of the Earth?
6 times 10 to the 24th kilograms.
Okay. And what's the radius of the Earth?
The radius of the Earth is 6.4 times 10 to the 6th meters.
And remember, we have to square this. So now, mumbo jumbo. Well, this kilogram will cancel out. This will be meters. Well, you square this meters. Well, we're doing the units first, just to make sure the units work out. So it'll be meters squared.
So you just get
So that will
meters on
cancel
it.
out. So now it's just meters over seconds squared. Huh.
That's the same as little g.
Yeah, that's the same unit that little g is in. So, see, little g is in a different g unit than big G. So, once you do all this math mumbo jumbo, you get approximately 9.8 meters per second squared.
Wow, that's amazing. And that's the acceleration for all things on Earth affected by gravity, right?
Yes, it is, Ben. Isn't physics fun?
It's so fun.
So, to review everything we've gone over, the mass of the object that's falling doesn't matter. It will accelerate at the same rate no matter what. And that's because the force on the mass equals mass times acceleration of the mass. And remember where we got the force equation from? It was G times m of Earth times m of the object over r of Earth squared equals mass times acceleration. Acceleration of the mass.
Oh, so you can cancel out those two masses because they're the same.
Yes, you can. And so then you have the acceleration of the mass is equal to all this, which is always constant when you're near the surface of the Earth.
That's called little g, or
Yes.
little g.
Little g.
Right. So the mass doesn't matter.
The mass doesn't matter.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Pop the molly, I'm swing. Pop the molly, I'm swing.